Hi, everyone. My name is Colleen Bertoni. I'm a computational scientist in the Performance Engineering Group at Argonne National Lab. And this talk is going to be about the different GPU programming model options on Polaris. So I'll cover part of the talk, the intro, and then the OpenMP offload part. And then Abhishek and Brian will cover topics which are other GPU programming models on Polaris. So we'll be switching back and forth. So let's get started. So first, to cover references, I wanted to point out a few other resources. First is the Argonne user guide for Polaris. There's a lot of information here. Also, the system Perlmutter at NERSC is actually quite similar to Polaris, and they have nice documentation, so I wanted to mention that as a resource. This presentation in particular used the slide reference here as a resource, so I wanted to acknowledge it before starting. Okay. So first, just to motivate and give some background for this talk. So this workshop is focusing on using Polaris, and the specifications are shown here. Adrian already went over all of this. The thing I wanted to say is that Polaris is a really powerful system, 19.5 teraflops per GPU, 1.6 terabytes per second memory bandwidth per GPU. However, how do we as developers take advantage of all the resources that are here? And that's where the programming models come in. These are the way we target the resources we want to use. And then, like as pointed out here, most of the computational power on Polaris is from the GPU. So we're specifically in this talk focusing on the programming models that let us target the GPUs. And we'll also be focusing on single node programming models for the CPU plus GPU part, just the single node shown here. Okay. So before we get started, I wanted to just reiterate on some background about CPUs versus GPUs in case people are more familiar with CPUs like I was before I started working at Argonne. And hopefully this will also shed some light on why GPU program models are structured the way they are. So just starting, a few comments on the differences between CPUs and GPUs. So a CPU is designed to reduce latency and run a single thread or a few threads very fast. This means the threads usually run at a high frequency and have hardware dedicated to decreasing latency, like branch prediction and out-of-order instructions. On the other hand, the GPU has been optimized for throughput, so it's optimized not for how fast a single instruction can execute, but how many instructions can be executed in a given time. So the example is something like a fast sports car versus a bus. Then with that background, I wanted to talk about the style of programming, since like we talked about, Polaris is a heterogeneous GPU plus CPU system. So your code starts out running on the CPU, and then it's up to you as a programmer to use the programming language or model to tell the CPU when to offload part of the code to the GPU, and then back to the CPU and GPU and so on. So in general, the part you'd want to run on the CPU is the part that's latency sensitive. Maybe it has a lot of branching in it, or it has to be run in serial, so then you run it on the CPU. And then the part of your code that parallelizes well, you want to run on the GPU. And then the other thing to keep in mind is that data transfer between the CPU and GPU is relatively slow. It's orders of magnitude slower to transfer data from the CPU to the GPU or GPU to CPU than it is just to be sitting on the GPU and touch the memory on the GPU. So usually it's best to keep data on the CPU if you need it on the CPU, or on the GPU if you need it on the GPU, and minimize data transfer. And we'll talk about how to handle data transfer with the program models once we get into more detail. Okay, so I wanted to say one more thing about GPU hardware, the Nvidia A100s here, since it's relevant to how the GPU programming models are structured. And again, to be able to use the GPUs on Polaris efficiently, it's useful to have a mental picture of this. So this is a graphical image of the A100 GPU from Nvidia's A100 white paper. So what we can see from looking at this is the larger GPU itself is composed of a lot of smaller repeated scalable units. This is actually true across vendors. AMD has dual compute units, Intel has repeated slices, and then for the Nvidia A100, we have these repeated streaming multiprocessors, or SMs. So that's blown up here just to show it's a bunch of the SMs. So the GPU is composed of a bunch of the smaller units all bundled together. All the SMs share some resources, so they all share like main memory, but they don't share all of the resources. So there's like no hardware to synchronize between two of the arbitrary units. And then the different resource sharing levels define levels of hierarchical parallelism, where the different levels are based on the resources that are shared at that level. So the coarse grain, the highest parallelism is between things running across SMs, and then fine-grained parallelism between threads running inside of an SM. This is important since the GPU programming models will usually give you a way to target the different levels of hierarchy if you want that fine-grained control. Usually this is useful for performance optimization, since, for instance, there's memory that's only on one SM, and targeting that memory is much faster than accessing main memory that all the other SMs share. And yeah, so with that background, this is the programming model landscape on Polaris. This is just listed here with the different programming models and which base languages are available in and what vendor supports them. I'm just going to do a brief intro of the ones that we're going to talk about, and then we'll go through most of them in detail. So first is the native model, CUDA. It's the main programming model for NVIDIA, and it gives you a lot of control over NVIDIA GPUs. It's also what other programming models are sitting on top of for NVIDIA. However, in CUDA isn't portable to other systems, so it's proprietary to NVIDIA and it will only run on NVIDIA hardware. So that's one thing to keep in mind. On the other side of this are the pragma-based programming models like OpenMP and OpenACC. These are usually really easy to get started with. They involve adding just a pragma as in the name, but sometimes they don't have as much fine-grained control of the hardware as CUDA, but they're generally very portable. So you can write code in OpenMP Offload, meant for NVIDIA, and then you can take the same code, compile it, and try to run it on AMD or Intel GPUs. So they're usually very portable. Somewhere in between are the C frameworks like Cocos, Raja, and Sickle. These generally provide a lot of control and are portable to different GPU hardware. Usually they're not vendor supported, like for Cocos and Raja. Sickle, on the other hand, is supported by Intel. We also do have OpenCL and Polaris, but we're not going to go into detail about it. But if you have questions about OpenCL, we will try to answer them or find someone who can. There also are AI or machine learning frameworks, but those will be covered later today in a different talk. And then with that introduction, we'll start with talking about CUDA, since it's the native model and the one that all the other models run on top of. So I'm going to switch over to Brian.
Hello, everyone. My name is Brian Homerding. I'm a computer scientist at the Argonne Leadership Computing Facility. I've been working on the exascale project, getting apps prepared for next generation systems. I also work with the Raja team for supporting Raja here at Argonne. So first, I'm going to talk about CUDA because, as Colleen mentioned, everything that's going to run on Polaris, most of the other programming models are going to run by sitting on top of CUDA. As we covered, it's NVIDIA's proprietary language. Kind of one thing to know is that it's computability 8.0 for Polaris. That's the A100s, just so that tends to be the only thing you need to change if you already have any CUDA code running, just to what you need to target for your compilation. It's very widely used and has a very robust toolchain. So that's part of the reason you build on top of the vendor supported library. Specifically, like the ECP models do this exclusively. It's because you want to have that good tool chain that's been long developed and has good reporting for bugs and all this. So you want to kind of leverage that work. CUDA provides support for C, C++, and Fortran. So you have a lot of options there. But as we mentioned earlier, it's proprietary and it's not going to be supported on the current upcoming DOE exascale systems that aren't running the Nvidia GPUs. So you're not going to be portable. I'm going to walk through very quickly a CUDA example. If you're not already familiar with CUDA, there's a ton of information out there on it to educate yourself. It's largely where people get started with GPU programming. But I just want to kind of walk through some of the key components for offloading a kernel, because you're going to see these come up again in the later models. So you can kind of see how all this fits together, and it's good to know about when you are trying to run it and figure out exactly what's happening when you go to kernel launch. So speaking of which, we have kernel launch. So this is basically when you actually are calling the function that you want to run on the GPU, kind of passing over the memory management parts where you need to make sure that the memory the device is going to use is accessible on the device, either by kind of manually transferring it or by using shared memory. You're going to need to define your iteration space. That's basically just saying, the size of the for loops for the kernel. In CUDA, you can define your kernel body as a separate function. It's going to get marked with special kind of attributes that help the compiler figure out what needs to get compiled for the device, what gets compiled for the host. And with CUDA, you're going to get your index, like where you are in the iteration space through the runtime by accessing these block dimensions and your IDs and your thread ID. So I'm going to very quickly go through hands-on on Polaris. So I put most of these commands in the GitHub for the SDL workshop. And then basically we're going to take a look at two little frameworks. I'm not going to walk through very much of them because lack of time, but Babel Stream, which is essentially the stream benchmark that's ported to many, many programming models. So if you're kind of interested in exploring programming models, it's a very nice place to start. And then the parallel research kernels, which is again, many different kinds of programming models implementing the same kernels. And it has a few different ones like DGEM, SGEM. Okay. So I already have a node, as you can see here. So I already have a few things downloaded. Going into Babel Stream. So Babel Stream is going to compile with CMake. So this is in the repo, but I have it here, so it's easier for me to cut and paste. Essentially, you're just going to define which model you need to load CMake always. You're going to define that we want to build with. So we're defining that we're going to use MVCC. So MVCC is kind of NVIDIA's main compiler. We have a few other ones like MVC, MVC++. Colleen's going to talk about those later. They're for OpenMP, but MVCC is kind of the original one, and that's what you're going to want to use for regular CUDA code. You can see we're running with CUDA 11.4. So the CMake command went through, and it's already made CUDA stream. So now we can run it. And as you see, we kind of are getting a good performance. This is what we've been seeing before when we kind of benchmarked the system earlier. You can a little bit of performance by up into the size that we're going to be running with. So that's very quickly basic command for compiling, but don't have time to go too in depth. In Babel Stream, you're going to have a lot of different models available, and you can kind of explore these as you like. But right now, I just want to walk through CUDA and get you running with your first kernel in case you want to test some of the profiling or anything like that. Also, we're going to compile Stream again with some of the other frameworks. The other one is the parallel research kernels. So as you see here, there's a lot of different programming models available. We're going to go into C++11, which uses C++11 features. And this is all online. So basically, you need to configure this project, build like everything. Here, I already kind of grabbed out what ends up getting spit out by the configuration, so we can compile it directly using MVCC. The main things here is that we're actually using cuBLAS, and we're able to pick up the BLAS libraries kind of naturally. It doesn't need to be specified. This is with the default modules that are available on the system. Then we get DGEM run. And we're going to be running on a single GPU right now. There's some versions that use multiple GPUs. You can kind of control which GPU you're running on with the environment variable CUDA visible devices. Unless you're controlling it kind of actively within your code. Okay, so you can kind of run through these by yourself. Always ping with any questions, just a few kind of nice places, especially with programming models to test with. And then also in the slides are a few of the pointers. So CUDA, NVIDIA has a lot of resources for CUDA. As expected, there's an introduction, and then of course the Polaris documentation. Next, I'm going to get into Raja and Cocos. So Raja and Cocos are ECP. They're from the DOE labs. They're basically performance portable solutions that tend to be header and library solutions. So they kind of sit on top of these other programming models, but they're meant to be widely portable. They're supported by the labs. There's no kind of direct industry vendor that's building them. And, the idea is you want to basically leverage the backend that supports the target system. So for Polaris, if you're really trying to get out your best performance, you probably want to use the CUDA backends, though you can also use the other backends on Polaris, especially helpful for if you're wanting to test things for moving forward onto different machines. So these work by utilizing C++ standard things, mostly like lambdas, to be able to basically take a generic kernel and map it down into the various backends for when it actually gets launched. So we're trying to get the best of both worlds by having the portability and having a uniform code while being able to leverage that vendor effort in developing their toolchain and the compilers. So they're pretty big projects. So I'm just going to talk about basically launching kernels like I walked through with CUDA, but there's a lot more. The Cocos has there's various libraries they support with algorithms and things like that. Cocos has some pretty big support for memory management, and you have various data structures. You have a lot of kernels and linear algebra kernels that are available. So to quickly kind of walk through what a regular kernel is going to look like. So this is their kind of starting point where if you need to write some code, you want it to run on the GPU. So this is XP kernel. This is from the tutorials that Cocos walks through. And you see a lot of the same pieces here that were in the CUDA kernel. So you're going to call it, it's a parallel 4. This is similar to the kind of Chevron launch from CUDA, just saying this is something I want to run on the GPU or wherever you're running when you're using Cocos. Nice thing is Cocos, because it's templated, and if you have ever debugged C++ template code, you end up going very deep with the template names. So this allows it to kind of plug in with profilers to get that name out and have it easier to identify what kernel you're running. You're going to have your iteration space. Your integer handle is now going to get passed in, so you know where you are in the iteration space, and then your loop body, which is captured in a lambda. So it's the same components, just kind of looks a little different. Next, Raja also has a wider suite of things. So Raja, the kind of core part that I'm going to talk about, is focused on kernel launch, and it doesn't have support directly for memory management. It expects you to kind of do the memory management elsewhere. There's a few other projects in the wider portability suite, Chai and Umpire, which do memory management, or you can directly use the underlying programming model, but then you lose some of that portability. So Raja loop execution is going to look pretty similar, with the difference being that there's going to be this execution policy template parameter. And that's going to say where you want to run it. Where in Cocos, when you build, you're going to define what Cocos backends to use, and Cocos is going to take care of that for you. With Raja, you're going to make some more explicit things, but it's all going to be in a header file. So when you port to a new system, you just add a new header file. So again, you're going to define the iteration space, and then you're going to have a loop body, and we're passing in the iteration handle. So once again, we're using a lambda to be able to capture that and pass it into a CUDA kernel launch. Okay, so this is again more on the GitHub that you can take a look at. You can clone Cocos and Raja, and then there's the Raja Performance Suite, which has many different programming models with implementations with Raja and without Raja. And there's actually very, very recent support for Cocos inside of there also. And I will go through a quick hands-on for this part. Okay, so we got Cocos. I have a built version already here and installed. So you can kind of go through this. It's on the GitHub. You can follow the instructions there. It's mostly just finding the right CMake command to build Cocos with. But instead, I'm going to go into one of their benchmarks. Now, one thing I did to kind of simplify working with it once I download it is I go into the MVC wrapper and I change this default architecture to use SM80. Just kind of simplifies things going forward. That's right up here at the top. So again, we're going to go for stream. See, I had this tested already. So All you got to do if you want to do this yourself is change these COCO's architecture to Ampere 80. So this was originally targeting a Volta, I believe. So you can go ahead. This is going to build all the components of COCO's that it needs. And then we're going to get a CUDA stream. Okay, then we get to stream CUDA. You can test this with the profilings to make sure it's running. I'm not going to step through that just yet because we'll have more of it later. But you also see we're seeing about the same performance as we saw with the CUDA stream from Stream. So the main thing is you benchmark these and you see that a lot of these programming model choices, you're not going to pay much overhead kind of using one or the other. And then for getting set up with Raja, with Raja, I put in a few different scripts. You can copy them in there. This is on the GitHub, basically. So you're going to have a build script and then a configuration, basically, to use CMake and actually get a build out of it. This will run through, probably should have left running. So we're going to compile everything. I'm going to run through one of their examples. They just have like tutorial matrix multiplies. I have it configured for building for a bunch of architectures right now, which I need to get fixed. But also for Raja Perf, you can pull that down and get that building. The same scripts should work for the most part. The thing with Raja is it heavily uses the sub modules for GitHub. So you're going to need to do a recursive clone, and that's going to pull down everything. So with Raja Perf, you'll pull down Raja Perf, and then you'll pull down Raja. And then inside that, you have these third-party libraries, and you have a few other projects like Camp. And actually, it'll pull down Cocos now for the Raja Perf. Okay, so here we're building the examples. So we're going to shortcut this and go in and just run one of the ones that's finished. So see, we have our matrix multiply. So this is going to run a bunch of different versions, just checking the results. This is because Raja, with that kind of template parameter, is going to give you a lot of control on how to run your program. So that's kind of the difference with Cocos, where Cocos says we're going to figure out what's good to run your program with and get you very good performance. Raja says, okay, you're going to have control, so you can do fine-grained tuning if you'd like to. And you can see here, we ran many different versions with CUDA, and everything's running well. Okay, and real quickly, you can get this from the slides. There's documentations. Both these projects have tutorials and communities that if you have any issues, you can ask with, or you can ping me directly on Slack. And with that, I'll hand it over to Abhishek to go into the cyclic programming model.
Thank you. Are my slides looking okay?
Yep, we can see you.
Okay, thank you. So in this section, I'll talk about the cyclic programming model, and thanks to Brian for providing the introduction to the CUDA and portability programming models such as Cocos and Raja. So cyclic is another programming model that is supported on Polaris. I'll briefly talk about what is cyclic and the libraries and the few practical aspects of how to use cyclic on Polaris. So cyclic is nothing but a C++ based programming model for intranode parallelism, similar like a CUDA OpenCL, initially motivated by targeting accelerators, in this case GPUs. So whenever people hear the word cyclic, it should be treated as a specification and not like a language. So in short, it is a specification wherein different compiler vendors will take that specification and implement it. And it should be noted that it's based out of C++11 ISO standards. And this picture on the right shows the active players or the vendors developing the compilers based off of this SYCL implementation. For the context of Polaris, we have compilers coming out of DPC++ driven by Intel. So this is an open source implementation of SYCL specification. As you can see, DPC++ is the compiler which can target CPUs, Intel GPUs, Nvidia GPUs, and AMD GPUs. So it covers pretty wide range of hardware platforms, and you can see other vendors as well targeting other accelerators. So DPC++ implementation of SYCL is available on Polaris. A few key features of SYCL, namely, is just cross-platform abstraction layer, and it's heavily backed by industry, as you can see. It's open source, most importantly, and it's vendor independent, as you can see, in contrast to the CUDA, which is a proprietary NVIDIA specific. One last thing to note here is it's a single source programming model, which in other words is it's the same C++ code that runs on both CPUs and any other hardware accelerators. So you don't write a different code or in a different file like in CUDA. So it just takes that complexity out. So the SYCL has been currently developed for other hardware accelerators in collaboration with Argonne, NERSC, and CodePlay software. And that as a result, we have a few compilers in good shape targeting NVIDIA GPUs. I'll just briefly go over the standard textbook example of how a SYCL programming model would look like in action. If you're familiar with the very old vector addition that you have seen in several programming models, it'll just follow the same flow. So if you just have a standard main with the host A, B, and C, as I'm showing the vector addition, C hosts the results. There are a few keywords here. If you see SYCL queue, and you will see a lot of this if you interact with SYCL programming model. As usual, you would allocate some device memory, A, B, and C. You would copy data from host A and B to device A and B that you just allocated, launch the kernel, copy back the results back to C on the host, and just print it out. So if you're familiar with any GPU-based programming model, all the steps are pretty much the same. It's just the syntax, which I would talk about how to automatically port. So in terms of heuristics, SYCL pretty much follows any other general purpose GPU programming model. So if you're familiar with CUDA, HIP, OpenCL, it pretty much is based off the same infrastructure and design. So the practical aspect here is on Polaris, we have three important modules. One is LLVM SYCL, which hosts a compiler, which provides the compilers. And I've just shown here what are the compiler flags looks like. Second is, what are the math libraries? Because without that, it would limit any practical use cases. So OneMKL provides the necessary math libraries to use SYCL and offload it to NVIDIA GPUs that are hosted on Polaris. The third advanced is the COCOS programming model. So as you have just heard that COCOS has several backends, CUDA, HIP, SYCL, targeting different backends. The advanced users who uses COCOS SYCL can use COCOS SYCL backend to offload it to NVIDIA GPUs as a change, and as a change to COCOS CUDA, traditional COCOS CUDA. So you can view this as a column of increasing complexity. So compilers, libraries, and COCOS programming model, which uses SYCL instead. Moving forward, this is just another example of when you run a SYCL programming model or a SYCL code and how to run it, what is the output. And this is just a quick snapshot of it. So as you can see, I have a few APIs. Everything, the documentation is available online. It's easy to follow. So this specific, the motivation behind showing this slide is how does a SQL programming model look like? How do you run it? And what does output look like by running it on Polaris? So if you see some of the keywords, it just says that, okay, give me the number of GPUs on that particular node. So it just says the first step is about discovering 4 GPUs. So this is nothing but like a CUDA get num devices. If you're looking for one-to-one equivalence in CUDA, you create a queue. So you should see this quite often if you're interacting with SQL. And in short, you just loop over all the GPUs available, sorry, and do some work on it. So this particular code just loops over all the 4 GPUs and then queries for what is the total amount of memory and what is the free memory available, and just prints that. You can see what are the compilation flags and all that. So if you have a SQL application, SQL programming model, all you need to play with is just change the makefile or the CMake lists and change the compiler settings and the flags needed. So that's the key step to actually give it a try on Polaris. And also talking about portability, because SQL was initially driven and developed for Intel GPUs, but now it has extended to other hardware vendors as well. So the slide talks about the 1MKL, which is the math library. As I said, like it would not be a complete discussion without the math libraries. So 1MKL is the open source project from one API. It has interfaces for math APIs. So as you can see in this chart, you have APIs for BLAS, linear solvers, random number generators, which in turn, when you run, maps to behind the scenes the CUDA-based libraries. So it's the same APIs, whether you run it on Intel or Nvidia or AMD or any other platform. They just offload it to the third-party, to the relevant third-party libraries. And I should just note here that the FFTs are in progress, which should have it supported in the due time. And one important thing here is, as I was saying, that SQL is not just a GPU programming model, it also supports hosts. So if you have written something in SQL using these APIs, it should also take advantage of the CPU-based libraries, which is Intel MKL, the traditional C or C-based, or the netlib. This is just an example of how a SQL programming model, which uses 1MKL, looks like. So traditionally, you just have the SQL header. In addition to that, you have a 1MKL header. Device discovery, you might be familiar with this from the past slide. This is memory allocation. Data transfer to the GPU. One new addition or one new call is the gem, which is using 1MKL gem. So you have, there are tools to port an existing cuBLAS usage to a SQL 1MKL as well, which I'll talk in the next few slides. So yes, when you run this using the instructions, and I'll just point out here that in addition to the standard C++ flags from the Clang, you just need to add one more flag, 1MKL, to just integrate 1MKL. And behind the scenes, it just uses offloads the code to the cuBLAS. That's pretty much it. It provides the source of portability with the libraries as well. And for the advanced users who uses Cocos as a portability layer, so this discussion might sound like a portability of a portability, because Cocos itself provides you the portability to different hardwares. So it's just like a portability of a portability discussion. So a user can test Cocos SQL, which was initially intended for Intel GPUs, but now you could just test Cocos SQL on Nvidia A100s as well. So there is a module, that's the information of the module to be loaded. And there is also a module for CUDA for comparisons. I would just like to point out here that the SQL is still very experimental, as you might see in the Cocos namespace. The module is also, the functionality is quite limited. So currently you could use it on the GPUs, and on the host side, there is it only works with the serial mode. So there is no OpenMP support yet. So in the future, this module would be updated with OpenMP support for host side. And this slide is just providing the resources. So the first two resources are just the SQL documentation for the APIs. And as I was saying, if you have an existing CUDA code and you would like to put it to a SQL or just explore what the programming model looks like, this link will provide the information and to just see what one-to-one mapping looks like if you're too familiar with CUDA. This second link provides the tool. And the math library I was just talking about, 1MPL is listed here in this, and this is an open source project. If you're keen on doing any hands-on with the SQL, offloading it to a Nvidia GPU, this GitHub is self-driven. It's a few examples of SQL that you could just compile and run everything on Polaris. That's all.
Okay, thanks, Abby. I'll take over screen. Okay, so I'll be doing the last section, which is OpenMP. So to get started, so OpenMP, so why would you use OpenMP as a program model? So it's an open standard for parallel programming. It's an API and environment variables that a lot of other vendors have implementations of. I think most people here are probably already familiar with OpenMP on CPUs. But I'm going to recap a little bit and then go through a little more detail about running on the GPU with OpenMP. So other reasons why you might want to use OpenMP. The big one is portability. So the vendors behind the other new supercomputers that are going up at NERSC, Oak Ridge, and Argonne, so Perlmutter, Frontier, and Aurora, will all provide OpenMP compilers and runtimes, and OpenMP will be supported on all those systems. So if you want to be very portable, it's a good option. And just for other few reasons for why someone might prefer to use OpenMP to something like CUDA, is that it's very easy to get started in OpenMP. It's basically trivial to parallelize loops. You just add a pragma, like we'll see later. And also it has some convenience functions like a reduction clause. So diving right in, so let's say you already went through all this work to parallelize your code with OpenMP for CPUs. So you found areas that were parallelizable, and for example, in this case, added parallel for or parallel do directives to spawn threads with the parallel and distribute iterations, and parallel and then distributing the iterations to the threads with the for directive. Then like we saw, a lot of the new systems are using GPUs. So the nice thing with OpenMP is that you can still take advantage of the work you did to parallelize with OpenMP for CPU, at least the starting point for running on the GPUs with OpenMP offload. So if you already know the regions you want to parallelize, you would change from parallel for to target teams distribute parallel for, like shown here, to target GPUs. But of course, maybe the first question is, what is the meaning of these additional pragma that we added for OpenMP offloading versus CPUs? And this is basically directly related to GPU hardware, so the hierarchical parallelism that I mentioned at the start of the presentation. So to understand this, we'll go through the clauses quickly, which will also tell us about the thread hierarchy. So the target construct is a construct that says to take any code that's inside an offload region and run it on the GPU with a single thread. It also transfers data with implicit and explicit rules, but for right now, you can think about it like the directive which changes from running on a CPU to running on a GPU. And the main thing to keep in mind is that although this runs on the device, it's running in serial. Of course, we don't want serial. We want to run more threads to take advantage of the GPU. So here we can use the teams construct to create a league of teams. Each team has only one active thread and all are running concurrently. This maps to the coarse grain parallelism. So these teams are running across the SMs in NVIDIA terminology. Then the parallel construct is what creates threads in the teams that can do things like synchronize with each other. And so this is kind of the fine-grained mapping. Then if we put it together and look back at this example, we have target teams parallel to create the thread teams on the device and distribute for to distribute the work. And then I wanted to go through a little bit about data transfer. This is important because it's much slower to access memory across the PCIe than directly. So data transfer from CPU to GPU and vice versa is slow. So I just want to go through this example in detail. So the target construct has some implicit rules for mapping types of data, and I'll mention a little bit of that. It's often recommended to explicitly note the data mapping with this map clause. The map clause is what says to copy things back to the device to the device and back from the device. So here it says to copy arrays A and B from the host to the device. That's with the to part. And then from, since it's mapped to from, back from the device. And then as you can see, there are some other variables used in the target region. So these are mapped right now with the default OpenMP settings, which means that the scalars like num and scalar here are mapped as first private and initialized to what they were on the host and are unique to each thread. And then loop variable J is defined in the target region and it's private to each thread on the device. And then the last slide before I'll do a very short demo is that with all the 3 programming environments, this is just a slide with the programming environments on Polaris, which support GPU offload. The default is the Nvidia compilers, and that's what we recommend. You can also switch to LLVM as well. The Cray compilers will offload, but it's not recommended. And the details about what modules to load to do that are at this link. Okay, so let me do some hands-on very quickly, stop share, and then I'm just gonna share my screen. Just this desktop. So can everyone see that okay? I hope, or can you guys see?
Yes.
Oh, thank you.
Yes, we can.
Yeah, so I already grabbed this from the GitHub, so the SDL GitHub, and there are some examples in here. The right side is the README file, which is in the OpenMP directory. So if you open that up, that's what's on the right. You can grab, so I already grabbed an interactive session, but it's here. So I'll go through the same examples for C and Fortran, and I'll just do one of the C examples very quickly. So the first one, which is just the very, very basic one. So that's 0, 1 target construct. So it's very simple. It just goes through basic target region and then using OpenMP to get some information about the device. So like we talked about, a CPU thread is running along, it hits the target region, and then it starts running on the GPU. Here, it checks if it's the initial device, which says, am I on the initial device, which was the CPU? And if that's false, which is what we expect, we get hello world from the accelerator, otherwise hello from the host, and then it exits. So I'm just quickly gonna run that. So there's a make file that will do this for you, and this is using the default NVIDIA programming environment. And then we can run this. Target. And this is, just to be clear, all on the README, so I can actually just copy and paste from there. And then we get output saying number of devices is 4, and hello world from the accelerator, which is what we expect. But just to double check that OpenMP is telling us what we wanted it to, we can do NVIDIA SMI, which is the NVIDIA tools to say what's on your device. So here we see I'm sitting on a node. I have 4 NVIDIA A100s, which is exactly what I expect and what OpenMP told us, so that's good. The one other tool I wanted to mention is Inside Systems. This is, again, an NVIDIA tool, which will give you information about kernel timing and data transfer. And it's useful to use for maybe larger applications, but for right now, I'll show just for this tiny one. So NSYS, NVProf, and then just the executable again. So like we can see, it tells us kernel statistics. So the OpenMP offload region, it gives you the function name and the line number and a little bit about memory operations. That example is doing almost nothing, so there's not that much memory. So those are 2 useful tools that we'll use in OpenMP or in generally on Polaris. And the other thing I wanted to point out by this is that OpenMP is sitting on top of CUDA. So tools that NVIDIA has for CUDA will generally work with OpenMP also, because at the end of the day, it's just sitting on top of CUDA. And then there are a couple of other examples in this directory. So feel free to try them out if you have time, and let me know if you have questions on Slack, and also Abhishek and Brian also for the program models they presented. And that's all I have. So thanks.